Okay, welcome to week 2 in review of NCEA Level 1 Mechanics. And this week we looked at interpreting velocity time graphs as well as distance time graphs. So if we take a look at question 1 from the 2013 paper, which is velocity time graph. For this question, we want to first make sure we understand what the graph is showing. So we have speed here on the vertical axis or y-axis, also known as velocity. And then we have time here on the x-axis. So time on the x-axis or the horizontal, and speed on the y-axis. The different sections of this graph you need to be able to interpret, and that is actually part A of the question. So part A of the question asks us to describe each section. So we need to describe each section. So sections A, B, C to D, and you must also use words as well as calculations. Whereas sometimes they just give you a question and they ask you to work out velocity. But if they give you the graph in this case, you need to be able to describe each section with words and calculations. So using words, so what I'm going to do is I'm just going to write the answer to that question all over the graph. So section A here, if you see a sloped line on a velocity time graph and it's sloping upwards, then this is showing acceleration. This is showing acceleration or positive acceleration. And the actual acceleration involved there is it goes from 0 to 10 meters per second. So for section A, we're showing acceleration, and we're accelerating from 0 to 10 meters per second. And the time that takes is from 0 to 8 seconds. So in 8 seconds, it accelerates from 0 to 10 meters per second. Now, if you want to actually work out the acceleration for that section, acceleration is given by the formula, the change in velocity over the change in time. So in this case, the change in velocity, it's final minus initial. So the final velocity is 10 meters per second, and the initial was 0 meters per second. So it's 10 minus 0, which is 10 meters per second, over the change in time, which was 8 minus 0 seconds. So that's 8 seconds. And that works out to be 1.25 meters per second squared, because it's meters per second per second. So that's the actual acceleration for section A. So accelerating at 1.25 meters per second squared. For section B then, section B is constant velocity of 10 meters per second, and that could be seen easily on the graph there. So section B, constant velocity of 10 meters per second. So we're just trying to use those numbers from the graph to support our descriptions here. And that is for a time period of from 8 to 15, so for 7 seconds. So section B, constant velocity of 10 meters per second for 7 seconds. Section C then, we can see that the slope of the graph is now sloping downwards. So this is a sign of deceleration. D-E-C-E-L-L-E-R-A-T-I-O-N, deceleration, also known as negative acceleration. If it's known as negative acceleration, then if we work out the acceleration for this section, we should get a negative value. And we do, because if you look at the change in velocity this time for section C, it's from 10 meters per second down to 0, which means that the final minus initial is going to be 0 minus 10 meters per second, and that's going to be equal to minus 10 meters per second. So you drop from 10 meters per second down to 0, and that's over a time frame of 5 seconds, from 20 to 5, so that's over a 5-second time frame. So your acceleration works out to be minus 2 meters per second squared for section D, or section C rather. So section C has a negative acceleration, also known as deceleration, of minus 2 meters per second squared. And then if you just look at section D there, well, in section D, the velocity is actually 0 meters per second for section D, which essentially means, which does mean that it's stopped. So it's no velocity, it's stopped. So that's how you would answer part A from question 1, 2013. Okay, in part D of this question, they ask you to work out the distance, the total distance covered by the runner. In this case, we're talking about a runner. So you want to work out the total distance covered. Now, the total distance covered can be determined by getting the area under the velocity time graph for the object in motion. And what you have to do is you just have to identify what type of geometric shapes you have and then work out the area by adding all those different shapes together. So if we take section A, the area under that graph is just a triangle. So if we highlight that triangle right there, that's section A. So the area of a triangle, if you remember from maths, is the half base by the height. So in this case, the base is going to be from 0 to 8 seconds. So it's a half of 8. And that's multiplied by the height, which is 10, from 0 to 10 there. So half the base by the height works out to be 40 meters for section A. For section B, we're looking at a rectangle there. So section B is a rectangle right there in that section. And then the area of a rectangle, section B, is just simply base by height, which is going to be from 8 to 15, so that's 7, times the height there, which is from 0 to 10 again, so times 10, which works out to be 70 meters. And then the last section, which is section C, that we need to work out an area from. We'll just use another color for that one. Section C, we're looking at a triangle again, so it's half the base by the height. And in this case, the base is from 15 to 20. So we're looking at this triangle right here. This triangle here is going to be 15 to 20, so it's the half of 5 multiplied by the height, which again is from 0 to 10. So that's 2.5 by 10, which is equal to 25 meters. And then there's no actual area under the last section, section D, because of course it stopped, so therefore there's no distance covered. So the total distance covered by this runner for the 25-second period is 25 plus 70 plus 40, which is equal to 135 meters. And that's how you use a velocity time graph to work out the distance covered by an object. Sometimes you get a graph which might have a shape which is composed of a rectangle plus a triangle, in which case the area for that section would be the rectangle plus the triangle on top. So you take base by height for the rectangle and half the base by height for the triangle and add them together if that's the kind of shape that you get. But that's how you work out the distance from the velocity time graph. And that's everything we've done this week, which would help us answer question 1 from the 2013 paper. Now we're looking at the 2012 question 1. At 2012, we were looking at a distance time graph. So we're looking at distance on the y-axis this time and time on the x-axis. A woman drives her tractor down a sandy beach to pick up a friend's boat. The distance time graph below shows part of the journey. So part A of this question was to calculate the average speed for the 90 seconds. So speed equals change in distance over change in time. And for this example, we're looking at the change in distance for the entire journey, which is from 0 to 600 meters there. So the change in distance is a total of 600 meters. And the change in time for the entire journey is from 0 to 90 seconds, so it's over 90 seconds. And that works out to be a velocity or speed of 6.67 meters per second. This section here on a distance time graph, by the way, if it's curving upwards, this shows acceleration on a distance time graph. If it is has a constant gradient, then this is constant speed. And then if it's a flat line on top, then it means that it's stopped, because of course the distance is unchanging there. It's still stuck at 600 meters. You can also use distance time graphs to work out the actual constant speed for section B there. So we'll do that now. So if we do it for section B, the velocity here is going to be the change in distance over the change in time again. The change in distance is from 120 to 600 meters. So it's final minus initial, so 600 minus 120 meters. over the time difference here, which is 90 minus 30. And so the calculation becomes 480 meters divided by 60 seconds, which gives you an average speed for section B of 8 meters per second. So that's how you use a distance time graph to work out the velocity of an object. And we also described what each section shows there. If the next part of the question is to describe the motion of the tractor in section B and explain what this tells us about the forces acting on the tractor during this time. Okay, so part B of this question from 2012 was to describe the motion of the tractor in section B and explain what this tells us about the forces acting on the tractor. Now, this just links us into this week's teaching, or rather week 3's teaching, when we talk about forces in relation to motion. But if we look at section B, we have constant speed, which means that we have a constant speed, and we worked it out there a second ago. The constant speed was 8 meters per second. So therefore, the speed is essentially unchanging. He's traveling at a constant speed of 8 meters per second for that 60-second period, which means that the forces must be balanced. The forces acting on the tractor must be balanced. And this is based on Newton's first law of motion. Newton's first law of motion, which basically states that an object will keep doing what it's doing unless one of the forces is on balance. So if we were to draw a little diagram to explain that, we would draw a tractor, and then the two main forces involved here would be the thrust force, forward thrust coming from the engine of the tractor, represented by that force arrow, and then the force acting against that would be resistance, whether it be air resistance coupled with the frictional resistance with the tires and the ground, and those two force arrows should be the same in size. So because these force arrows are balanced, there is no change in motion, and you get a constant speed of 8 meters per second. And that's Newton's first law of motion. You also needed to, I looked at the answer scheme, and you also needed to mention that the forces were acting in opposite direction. So the forces are balanced, acting in opposite directions. It's kind of like a tug of war where both people involved are of equal strength. And you could also say that the net force is equal to 0 newtons. So there's no force in either direction overall that's greater. So its net force is equal to 0 newtons. Now, as I say, this is a nice link into this week's teaching, where we'll talk about forces and their influence on the motion of an object. And that's week 2 in review, acceleration and velocity, and relating them to velocity time graphs, distance time graphs.